Welcome back. Today we're going to begin calculus proper in the sense that we are beginning integration theory today. And I want to talk to you about the very beginnings of integration theory in the real context. I want to talk to you about how it works sort of on a very high level. And I want to talk to you about some challenges that we will have translating that to the complex case. So let's talk about the most important theorem of calculus, the fundamental theorem of calculus. The fundamental theorem states that the integral of a derivative gives you the total change in that function. So there are two versions of the fundamental theorem, but this is the one that I want to focus on today. Either version implies the other one. So if we have this theorem, so how do we prove this? Well, typically when we prove this theorem, we invoke the mean value theorem. So let me remind you what the mean value theorem says. If we have a function f, it's differentiable on a region AB, slightly weaker hypotheses will work. Then given the values of f of a and f of b, we can form this difference quotient, which is the slope of this secant line connecting a to b. Now that slope will match the slope of some tangent line for some c value here, which is between a and b. So why is the mean value theorem important for proving the fundamental theorem of calculus? Well, when we perform the integral, then we're effectively breaking this integral up into segments and approximating them by rectangles. And the mean value theorem comes into play because when we analyze each segment, we get an equation like this. F of xn plus 1 minus f of xn divided by xn plus 1 minus xn is equal to f prime of c for some value of c which is in between. So that's c. And notice this is the graph of f prime. So f prime of c is simply the height on that graph in this picture. Now, why is this equation so significant? Because this relates the total change in f to the rectangular estimate, f prime of c times the width of that rectangle. So this is the total change, and this is a rectangle estimate, which is an estimate of the integral. Now, this isn't a complete proof of the fundamental theorem of calculus, not by any means, but it does indicate how and why the mean value theorem comes into play. This is the total change only on a small region. We have to sum them all up over the regions. This is only one rectangular estimate. We have to sum them up. And then the fact that it's an estimate, then we have to deal with how closely it estimates, and we have to control some error here. So this is not a complete proof, but it does show how we are using the mean value theorem to produce some useful information toward the proof of the fundamental theorem of calculus. And so that's the typical way of moving toward the fundamental theorem of calculus in the real case. Now, there's a problem with the mean value theorem in the complex case. The problem with the mean value theorem is this notion of betweenness, a less than c less than b. If we have two complex numbers a and b, then there is no corresponding notion of betweenness that applies in this sense. So we cannot simply say that a complex number is between two other complex numbers. We don't even have a version of less than that applies consistently to complex numbers. And so we can't really make sense of this statement of the mean value theorem. Nevertheless, what the mean value theorem is really doing for us is it's allowing us to relate difference quotients, f of b minus f of a over b minus a, to derivatives. There is an obvious and preliminary, there's an obvious start for this relationship, which tells us that obviously they're going to be connected because the derivative is actually a limit of difference quotients. And so just the fact that the derivative is a limit of difference quotients is already a connection here. But notice that this is not just a limit of difference quotients here causing this thing to be equal to this, because this is a true equality here, not an approximation. And C is neither of these endpoints, B or A. And so the power of the mean value theorem is that it gives you equality even when we don't exactly have the right correspondence you would expect if you just applied the limit definition of the derivative. C is not A, as you probably would expect it to be if you were trying to leverage the limit definition of the derivative to get an approximation. So the mean value theorem is hard to use in the complex case. And so what does that mean? When we develop complex calculus, often what happens is we have to invent complex integration, and we have to describe how that works, and we'll have to do that. We invent complex integration, and then we have to prove some sort of complex fundamental theorem of calculus. Often what happens is this complex version of a fundamental theorem of calculus is proven by using the real version of the fundamental theorem of calculus, which is proven by using the mean value theorem, which doesn't apply in the complex case. Now, that's all well and good for students who have already had a rigorous real valued calculus that proves the fundamental theorem by means of the mean value theorem. For students who haven't had that, that's not really an adequate approach, because that requires in the complex calculus, in the complex analysis course, we have to develop the whole theory of integration twice over. We have to do it for the real case first, and then we have to do it again for the complex case. And I don't like doing anything twice, not in mathematics. And so what we're going to do instead is we're going to develop a theory of integration which applies to the real case and applies to the complex case equally well. And so we're going to get a sort of a unified theory of integration. Now, that's the advantage is that we only have to do it once. The other advantage is that now you will kind of be able to convert that into a real theory if you want to understand the real theory. Maybe you're going on to high school and you really want to understand how the calculus in high school is founded, then you can use this theory to inform how that really works underneath everything. So that's the advantage of that. The disadvantage of this approach is that it's a little bit complicated, and it cannot rely on the mean value theorem anymore, because the mean value theorem per se is not really sensible for complex numbers. And so what we're going to do is we're going to build toward something which is effectively a replacement of the mean value theorem, which works more generally than the mean value theorem and doesn't rely on this notion of between and doesn't rely on inequalities. This theorem is a sort of a uniform approximation of difference quotients by means of derivatives. And it's all about the relationship between the difference quotient and the derivative. And so to work toward this theorem, what we're going to do is we're going to introduce a function, which I will call Q for quotient. And that's a function that's just meant to hold the difference quotients and the derivatives all together in one. So let's define this function Q and see what we can do with it. So let f be a function defined on a subset of C or R. And let's let Q of W and Z be defined to be f of W minus f of Z over W minus Z. Now, so that's not quite complete, because that's not defined if W is equal to Z. And so let's say it's going to be this if W is not equal to Z. What should we define this to be if W equals Z? Well, the limit of that. And so we'll define that to be f prime of Z. It doesn't matter whether we say f prime of Z or f prime of W if W equals Z. So, so we'll define this to be the difference quotient if the values are different, and the derivative if the values are the same. That way, when W approaches Z, then this will be a continuous function, and we will get the value f prime of Z. So if we name the subset defined on, let's assume that we have an open subset U of R of C or R, then Q maps U cross U to C or R. So it's defined on U cross U. Now, is this function continuous? Well, that's a difficult question to answer. It looks like it might be an easy question. So notice that on the set of all WZ for which W is not equal to Z, so Q is continuous. Q is then a combination by subtraction and division and more subtraction of functions that are known to be continuous. I should assume here that f is going to be a differentiable function. So if f is a differentiable function, then this exists. And if it's a differentiable function, then this is continuous as a function of W. This is continuous as a function of Z. And these operations are continuous, and they're continuous where they're defined, which is where W is not equal to Z. So on this thing, Q is continuous. And it's a continuous function of two variables then. So furthermore, the limit of q of wz as w approaches z is nothing more than the derivative, which is q of zz. And the limit as z approaches w in exactly the opposite way is going to be f prime of w, which is q of ww. And so it looks like, so this gives us limits on the diagonal on the places ww or zz coming in horizontally or vertically. And so it looks like we have continuity, but we don't. So what we have here is that q is continuous for each w as a function of z. And it's continuous for each z as a function of w. And furthermore, I should point out that q is symmetric. Q of wz equals q of zw. Now, why doesn't that entail continuity? Well, let's make a chart here. Let's call this u cross u. And then q is a function here, which maps into the complex numbers. So we have this problem on the diagonal. And so when we assert that it's continuous for each w as a function of z and continuous for each z as a function of w, what that means is on the diagonal, we can map this to some point, f prime of z. So this will be a point zz on the diagonal. And then the continuity as a function of w means that for every ball here, if you take a ball around f prime of z of radius epsilon, then there is a delta ball here for fixed z. There's a delta ball in w, and there's also a delta ball here for fixed w. There's a delta ball of various values of z, and both of those w balls map somewhere into this epsilon ball of f prime of z. But that's not the same as saying that there is a ball here or a rectangle here, which maps into the same. And that is what we would need in order to assert that q is a continuous function of two variables. And so, yes, it's continuous in each variable for fixed values of the other, but it's not yet known to be a continuous function of two variables. And that's something that we'll need to work on. So this gives us the function q. Now, what are we going to do with it? We're going to use it to give uniform approximation of the derivative using the difference quotients. Now, the first thing that we're going to do with it is we're going to prove a theorem about what happens when this thing is known to be smaller. So basically what we're going to prove is that if the derivative is known to be small, then the difference quotients are also going to be small. So in this case, we need the domain to be an open and convex subset. So this is the form of the theorem we're going to prove. If f is differentiable on a set x, which is both open and convex, in R or in C, and if the derivative is bounded, either in absolute value or in modulus, for all the z in that set, then this function q, including all the difference quotients, are equally bounded by the same value for all w and z in that same set. So in order to prove this, we're going to prove a sort of a transitivity statement along straight lines. So proof. The first thing that we're going to do is we're going to claim, so if w and z are in the set x, and m is on the straight line segment between them, and if the modulus of qwm is less than epsilon, and furthermore, the modulus of qmz is less than epsilon, then the modulus of qwz will be less than epsilon. So we're basically, let me draw a picture of this. We're sort of stretching these difference quotients out across a straight line and proving a sort of a transitivity property. So let's draw a picture. We have a point W. We have another point Z. Let's space it farther away. We have a point Z, and we have a point M on the straight line segment between them. So the difference quotient here is going to be small, and the difference quotient here is going to be small. And we're trying to show that the difference quotient, f of z minus f of w over z minus w, is also small. So this is actually going to boil down to basic properties of fractions. Let's see what happens. So we've got q of wz, which is equal to f of z, let's start with w, f of w minus f of z over w minus c, modulus. What we're going to do is I'm going to add and subtract f of m and m here. So this is going to be modulus f of w minus f of m plus f of m minus f of z. And then this is going to be w minus m plus m minus z. And now I'm going to apply the triangle inequality, and let's be very, very careful as we do this, because we're likely to make a mistake. So I'll apply the triangle inequality to the top and to the bottom. Now, this is, you have every right to say that's probably a mistake. This certainly looks like a mistake. The triangle inequality applies to the top and tells you that the modulus of this sum is less than or equal to the modulus, the sums of the moduli of the individual parts. And so that's the usual way that we apply the triangle inequality. What I'm doing on the denominator seems, well, seems backwards, right? Because when I apply the triangle inequality to this thing, then it should get larger, and that should cause the fraction to possibly get smaller, which means that this same act performed on the denominator should cause the opposite inequality, and so doing it to the numerator and the denominator should cause an unpredictable relationship here, and I shouldn't state the equality sign. That would be true for most cases, but there's something different about this case, and that is that m is on the straight line segment between w and c. And if it is, then this is nothing more than the distance between w and z, and this is the sum of the distances from w and m and from m to z, which is equal to, not less than or not greater than, not less than or equal to, but the sum of those two distances is equal to the total distance precisely because m is on the straight line segment. So in the denominator, we actually have an equality, and in the numerator, we have the less than or equal to that we need. And so now what I'm going to do is I'm going to argue about these things. Now here I have this looks like, let me do, forgive me, let me make a naive mistake. So this is going to be q of wm plus q of mw, right? Of course not, right? This is a silly mistake, but it's a useful mistake to understand what should happen next. Of course, the sum of two fractions like this is not going to be equal to just add the numerators and add the denominators. That's a very naive mistake. What is the relationship between two fractions given like this and the sum of their numerators and the sum of their denominators? Well, there's a general property about fractions. So note, if you have numbers a, b, c, and d in, I shouldn't write this here because I'm going to have to erase it immediately if I write it here. So let me put it over here. So if a, b, c, and d are in the positive reals, and if a over b is less than c over d, then what does happen when you naively add the fractions by adding the numerators and adding the denominators? Well, what actually happens when you add numerators and add denominators is you get, let's make these less than or equal to. What actually does happen here is you get a number in between the two fractions. So, so this is what happens in truth. And the reason is very simple. Any inequality among these fractions with the denominators non-negative, well, positive, can be, we can just clear the denominators and get an inequality between products. So this inequality between the fractions is equivalent to the inequality AD is less than or equal to BC. It's equivalent anyway if they're all positive numbers. So this inequality is equivalent to this inequality. Well, this inequality here is equivalent to the inequality AB plus AD is less than or equal to AB plus BC, right? Here I've multiplied both sides by B plus D and multiplied both sides by B, and I've got this. Well, notice that the AB's cancel, and this is the same statement as this. So if this is true here, then this is true, which justifies this inequality, and the other one is similar. So this is just a basic property of numbers, that when you have positive values here, and you add fractions in the silly way that isn't actually adding fractions, you add numerators and add denominators, you end up with a positive fraction which is in between the two. Now, our assumptions for QWM and QMZ are these, that QWM is less than epsilon and QWZ is less than epsilon. And so this thing is certainly not the sum of the two fractions, but it is between those two values. So this thing is between QWM and QMZ, the two values that we've made assumptions about. And each of those is less than epsilon, and so this entire thing must be epsilon. So it must be less than epsilon, and we can conclude by connecting the dots here that QWZ modulus is less than epsilon, which was the content of this claim. So this doesn't prove the theorem. The theorem is, what we're trying to do is we're trying to show that if the derivatives are always less than epsilon, then the difference quotients are always less than epsilon. And this shows us that if the difference quotients along a line are less than an epsilon for step 1 and less than epsilon for step 2, then they're less than epsilon for the combined step, which is kind of the conjunction of those two steps. So now what we're going to do is we're going to try to reduce this to topology. So let's pick a value, z, and what we're going to do is we're going to try to show that for all w's, then we will get this thing less than epsilon. So now that this claim is established, I'll erase this part of the proof, and we'll try to continue. Actually, let's fix a value w now instead of z, and then we'll try to argue about what happens next. So fix, actually, let's fix w and z in the set x. And let's let I be the closed interval, the closed line segment connecting w to z, and then of course notice that I is a subset of x. That's why I had to assume that x was convex. Convex means if you connect any 2 points by a straight line segment, then that segment lies within the set. So that's because x is convex, and that's the only reason I needed to assume that x was convex here. Star-shaped probably would have worked too, but I'm not sure. So yeah, maybe not. So here we have some interval here, and that's the interval drawn here. So basically, this whole thing here is now the interval I. Now, next I want to consider that for some of the m's in between, this theorem, the conclusion here might be true, and for some of the m's in between, it might be false. And so let's consider the m's for which it is true. So let's let S be the set of m in I, so that what's true? Q of Wm modulus is actually less than epsilon. So basically the m's for which this conclusion, Q of Wm less than epsilon, is actually true. This could be empty for all we know. But in fact, we know that we can conclude that this is not empty by using the fact that W is a possible value for M, right? So notice that W is in S because f prime of w modulus is less than epsilon by assumption. And this is one of the possible values of q, right? Q of ww is f prime of w, which is assumed to be less than epsilon. So this set S is non-empty. Now let's think topologically. S is an open set. Why is this? Well, it's an open subset of I, that is. Why is S open? Because S is the preimage of the set from minus infinity to epsilon under the continuous function, which is the modulus of QWM. Notice that modulus is a continuous function, and Q is continuous in M for fixed W. And so this is a continuous function. So we have a preimage of an open set under a continuous function. So S is an open subset of I, that is in the relative topology of I. So it's an open subset of I. And I is compact. And that means that I minus S is also compact. Now, I hope that I minus S is empty. But if it's not empty, since it's compact, it will have a point in it which is closest to W. So it will have a point with minimal distance from W. So if I minus S is non-empty, then let's let M naught be the element of I minus S closest to W. So let's draw M naught. Let's say it's here. The first thing we should be concerned about is perhaps M naught is W, right? But that's impossible because we know that W is in S. So it will be some different point on this interval. Perhaps it's Z itself, I don't know. But it will be closest to W in the sense that everything prior is going to be in the set S, but M naught is not going to be in the set S. Now, this M naught point may be a problem for us, but we do know that the derivative there is less than epsilon. So notice that the f prime of M naught modulus is less than epsilon. So for some x near M naught, but between W and M naught, what we have is we have Qx M naught modulus less than epsilon. Why is this? Because f prime of M naught is the limit of this as x approaches M naught. There is some neighborhood of M naught for which these difference quotients must therefore be less than epsilon. And so we're going to pick an x in that neighborhood, but also on the W side of M naught. The fact that it's on the W side and not equal to M naught means that it's closer to W than the closest point in the complement of S. And that means that x is in S. Now, what does that mean? So x is in S, so the modulus of QWX is less than epsilon. And now by this claim about transitivity along straight lines, we have the difference quotient here less than epsilon and the difference quotient here less than epsilon. And so we apply the claim and we get the difference quotient between W and M naught itself is less than epsilon, which is a contradiction. It's a contradiction to the assumption that this is empty. So sorry, that that's non-empty. So thus, I minus S is empty. And that means that Z is in S. What does it mean that Z is in S? It means this. So it means the modulus of QWZ is less than epsilon. Now, W and Z were fixed but arbitrary in this set, and we just showed that the difference quotient QWZ between them is less than epsilon. And this establishes the claim that the difference quotient for any two values is less than epsilon. Now, this gives us that if the derivative is small, then the difference quotient is small. And the first use to which we can put this is we can prove that if the derivative is 0, then the difference quotients are 0. So let's deduce that corollary quickly. So I think we'll put it right here. So corollary of this is that if f prime of z equals 0 on an open set X, then we have, then f is locally constant on X. Now, I should be careful here. Just because the derivative is 0 on an open set doesn't mean the function is constant. If the open set is the union of two different regions, then it could be constant here and constant here, but not constant because it takes two different constant values. So what we mean by locally constant is for every point in X, there's a neighborhood and it's constant on that neighborhood. So if the derivative is 0, then the function is locally constant. Why does it follow from this theorem? Because we can apply the previous theorem for every possible value of epsilon. So for every epsilon greater than 0. And what does that produce? The hypothesis that f prime of x in modulus is less than epsilon is true for every positive epsilon. And so what we deduce is that QWZ is less than epsilon for every epsilon. And so what does that mean? That means that it's 0. So the modulus of QWZ is equal to 0. But we should be careful here, because I've applied this theorem, which only works for open convex sets, and I've applied it to an arbitrary open set. So how does this work? This is not actually true on all of X. It's true on every neighborhood. So that's on each ball. So on each ball B x naught delta subset of X. So this fact that the difference quotients are all 0 is true on each ball. And now if the difference quotients are 0, then the function is constant. So f is locally constant.